5 to 18.
Yeah.
Look at me remembering numbers and stuff. Okay, so let's see. Oh, so this is the one where they want you to change that to the elongated S form of things.
Oh, they just want you to define it as that?
Let me see, hold on. Come on, work with me. There we go. Whoa, well that's, oh I see. Well that's the carpet, that's neat. Okay, so this one, is that already better? Is that what I'm hearing over there?
No, I was thinking that I had to like solve and
No.
yeah, and then I got
That would be
yeah
insane.
yeah no
Yeah. So this is a really good example of a function that we look at it and we go, I don't want to use the definition of integral, right? Sort of like the definition of derivative for certain functions would be basically impossible for us to do, yes? But this, all they want you to do is rewrite that from infinite sum to what we represent an infinite sum with, which is just a long S. I like that idea. They just were like, there we go. Take an S. There. That's infinite S. Okay. I kind of love that, let's be honest. Anything else, Faye?
Section 4.9, number 66.
Oh, yeah. Motion in a straight line with, so they give you that there's constant acceleration, right? So that means I can write something very weird looking. I can write, well, let me make it a little less weird. I think I wrote this last time. There, right? Constant acceleration. How do you get from there to the velocity? What do you do to get to the velocity? Yeah, antiderivative, right? Jeff, there's put AD. So what's the antiderivative of a constant? AT plus C. But what did they tell you the initial velocity was? Initial meaning time equals 0. You can solve for C because they told you at time 0 the velocity is what? They didn't tell you a number, but they just told you it's VO, right? V naught. Yeah. So when time is 0, you know that this is V naught. Okay, that's all I'm going to do. I like it. So then it's just a couple of steps of that same thing. And if anybody has physics in their future, this is kind of like creating the kinematic formulas. You don't have to know that word kinematic right now. Okay. Anything else? Homework stuff? 54?
Yes.
Oh, yeah. Oh, yeah, okay. So, what, have you tried anything yet with this?
No.
Which property kind of embodies this idea? Between what two values must this lie? I mean, there must be a property then that looks like what? If I want something to be between two things, it must look like an inequality, right? So which property deals with capturing the integral between two values? Not quite. I appreciate that. We're going to use the squeeze theorem today, by the way. This one here, see? Yeah. This one seems very strange, but I love this. I love this. Let me write it down here. Talk about it just for a second. So if m less than or equal to f of x less than or equal to m, then the integral, right? Holy shit, I love it. You guys are all like, he'll figure it out sometime. Right? If this function is between these two values, then the area under the function has to be, now let's see a visual of this. So if I have a function, okay. So isn't that function between this output and this output? Yes? Okay. So what if so this is just saying, what if this was just always this? What if it was just always this? What would the area underneath it be? Wouldn't it just be m times b minus a? Is that cool? So that's this side. And if it was always m, wouldn't the area be big ass m times b minus a? So the area that is actually under this function is going to be between this area and this area. It's just a beautiful visual, right? Of course it is. It's kind of like, when you see it, hopefully some of you guys are like, well, yeah. Pretend like it's a little box, pretend like it's a big box. And that's why the outsides are so nice and simple, because they are rectangles. And the seams, so this is so nice and visual and blah, blah, blah. And then you're like, what the shit am I supposed to do with that? But there's a couple of homework problems where you get pretty decent approximations when you don't even know how to do an integral yet. You can get decent approximations. It's between this, and it's pretty good. Okay. Is that? Now the real power of this is going to be when I use it to prove theorems. Sort of like mean value theorem and all that kind of stuff. By itself, it was like, okay, but then we use it to prove theorems. That's where the real power comes in. Is that better? Is that right? Yeah? Anything else? Homework? Okay, all right. So, today is exciting. Today is a big day. No idea how you guys feel about what I'm saying.
Which chapter are we in?
We're in chapter 5 still, and we're in section 5. What section is this? 5.3. I don't know sections, I just know math. I don't know. Yeah, 5.3.
So no quiz on Monday then?
Say again?
No quiz on Monday?
Oh, I don't, No, let's have a quiz on Wednesday. How's that sound? Better than Monday? You want Wednesday or Monday?
Wednesday.
Holy shit. And we'll do it through 5.3. Haha.
Oh, so just 4.9 through...
4.9 through 5.3.
Okay.
Yep. So, let's see. You guys all heard me. I'll put it up here for the video. Quiz. Wednesday. 4.9 through 5.3. Chua. So, of course, that's going to include that whole process of finding areas, integration, where you have to know the I formulas, which I'll obviously give to you, right? It's not so obvious when I can't say the word obvious. All right. So, today's a big day because this is when we make the connection between antiderivatives, which can be very simple. We've done a lot of antiderivatives so far, so they can be pretty simple, but they can very quickly become close to impossible. Antiderivatives and integration. So on the surface, these shouldn't necessarily, and integration, of course, is just the process of finding areas, right? Let me put that next to that. So the integral, I think I've said that word, so the integral is this symbol here. Okay. So this is a huge connection to make because this gives us a shortcut. Instead of doing that whole summation thing and get the I stuff and move the N stuff and replace it and do the limit, right? That crazy thing. We're going to make a bit of a shortcut by connecting it to a process that's relatively simple, at least at the moment. Okay. So how are we going to do that? So the very first thing we got to do is we're going to create a new function based on a process that we know. Can somebody tell me what would, all right, so just remind me, what does this function, what does this process do for a function? Finds the area. Where? Under F, between A and B. And of course, when I say under F, let's make that a little more precise. Between the x-axis and F. So if F is under the x-axis, that officially gives us what I go ahead and call negative area, and what some people don't like when I say that, we're sophisticated enough to understand it's not a physical area. So that's why it's okay if it's a negative thing. It just means I'm losing some amount over time instead of gaining some amount over time. Okay. So we're going to create a function out of this. Everybody understand? This is not a function currently. This is a process if I give it a function. Yes? It's a process to find the area between the x-axis and a function. So let's create a function like this. Let me see if you guys are cool with this. What I want to do is, all right, let me start like this. What I want to do is, I want to say, okay, I can find the definite area, and I kind of say that on purpose, like the definite integral. I could find the area. That's basically what that is, right? But what I want to do is I want to set up a function so that I could find the area at any place in between these two. So I don't want to, I want to say, I want to let the endpoint be a variable. I don't want to go from a number to a number. I want to go from a number to a variable. That would make it a function. So like if I plug, so for example, if I plug a C in, it would give me this area. If I plug a D in, it would give me this whole area, right? Okay, and right now you might be like, why the hell would you want to do that? But just kind of, we like to make things into functions. So we're going to do more general things with them. Do I know always what I want to go from to? No. So the way we're going to do this first step is a little strange. And that could be like the tagline of this course, but first step's a little strange. So what I really want to do is let me see if you guys are cool with what I'm about to say. So I've got some A to B, and I've got some function. And what I really want to do is I want to say that is my variable. So I want to integrate from A to X, where X can be anything in between A and B for the moment, right? Let me stop for a minute. Is that all right? Okay. But in order to do this, what I need to do, can I call this the x-axis then? Can I call this the x-axis if x is actually kind of its own variable? I don't know if you guys really understand what I'm saying. If x designates a specific spot on that axis, can I call it the x-axis? Do you guys understand? No, I cannot. Because now x means like 7. It can't mean anything on the axis. It means that specific thing. It could change, but it can't represent everything anymore because now it represents where I want to stop. I don't know if you guys are really with me in this. This is one of the weirdest things about getting into this discussion is we have to call this a different, we're going to call this, yes?
Wasn't there some really cool name for the x and y axis? Like when Descartes like originally made it. I forgot what it was, but There's some like 3-syllable word for the practicing law.
I don't know. I'm not sure if I ever knew, but that sort of sounds familiar. I don't know. If you figure it out, let me know. Because I'm always big into, well, I've done a really pitiful job of it this semester, to be honest, but I'm normally pretty big into the history of things. And what really kind of sucks for you guys that I was realizing the other day is I normally have this timeline of mathematics, and I just completely forgot to throw that up in Canvas so I can reference it. But I got this timeline of mathematics, and I like to point out all the contributions from other civilizations and men and women or whatever, right? And I completely forgot. That's fantastic, Jeff. This semester, everything is weird this semester. Come back to campus, so I'm trying to give myself a little excuse. But I normally do like to infuse a little bit of history in. Those kind of things fascinate me. Like, why does the square root symbol look the way it does? Stuff like that. All right. So if you find out, let me know. So we're going to call this axis the t-axis. And again, we should have zero trouble with this because variables we call them dummy variables. It doesn't matter what symbol I use. I just have to know what the symbol represents. So this symbol represents anything on this axis. This symbol represents a specific part of that axis that I want to stop at. Okay, so now this function is f of t. So now I'm going from a to x. Did I really change the function at all? Now, I kind of did because I didn't draw the same thing, but pretend like these are the same. Did I really change the function at all? No, I just changed the letter that represents the inputs. I didn't change shit, right? So if I said f of x equals x squared, and I said f of t equals t squared, are those fundamentally different? No. Just the symbol that represents the inputs changed. That doesn't change anything. Okay. Do you understand now that this is a function now? Right? This is a function because if I change x, I will get different outputs. So if I make x b, I'll get this whole area. If I make x some number c in the middle, I'll get a smaller area. So I can call this g of x. So g of x is sort of the area up to x function, right? The area from a up to x. And what is x? Whatever you want it to be. All right, let me stop for a minute.
Can x be b?
Yes, x could be b. Could x be a? Yes, x could be a. Could x be something below a? Yes, x could be something below a.
How about above b?
Above b, yes. So, but if I want to do that, the reason I'm kind of sticking between a and b at the moment is because when I kind of do this, I go into it knowing that f of x is continuous on a, b. So as long as my x, a to x, stay with me now, not just continuous, but remember it could be finite jump discontinuities. Do you remember that? So as long as it's integrable, there's that word again, integrable between a and whatever x I want to choose, it's fine. Which kind of makes sense. If the function is defined based on an integral, then the function is only defined when this is integrable. Okay, I like it. You guys okay out there? No? Okay. It's about right. It's about where you should be. Okay. So let's do something really specific. Very concrete. You want to do something really concrete? You're like, please, dear God. That would be so cool. You could stay right there. So I'm going to look at number 3 on page 399. So they have set up a function to be the area under f of t from 0 to something, whatever I want it to be. So let's do part A together. All right, let's see how I can do this. Put you there. Gonna have to zoom out a little bit. Okay. Let's do this. Let's push you there. I really hate doing things on the overhead, but too bad. All right. I can go in a little bit. I want to keep notes on this. Okay, so everybody stay. G of 0 should be easy. Just plug a 0 in, right? So again, fundamentally, g of x is like any other function, but it's based on the process of finding areas. So when you have a different input, it goes to the top of the integral, and then it tells you where to find the area between. So of course, what would g of 0 have to be? 0, right? Is that cool? G of 0. G of 0 technically would be 0 to 0 integral. And everybody needs to really understand that the area between a number and itself is 0, of course. It's got no width. Okay, I love it. Now, can you take a minute, maybe not a minute. You don't have to do any summation work. You don't have to do any antiderivatives. You don't have to do any weird shit. What shape does it make for the area? Because again, the g of x is the area from 0 to the input. So what, of course, if I put a 1 in, what shape do I get? Little rectangle. And what's that guy's area? 2. I love it. Okay. Integral 0 to 1, f of t dt equals 2. So the area so far that we've picked up as we move, so I kind of like to think of it as scanning the function. As I scan over here, I've picked up an area of 2 so far. Now, to do g of 2, can't I do, so that means the area up to 2, correct? So this officially would be this. But isn't that going to be from 0 to 1 plus, Jeff, from 1 to 2? So isn't that going to be what I've got so far plus what I pick up as I keep going? So that's what this says. In fact, the area from 0 to 1 plus the area from 1 to 2 is the area from 0 to 2. Yes? And I believe that was one of the properties we discussed last time in our big-ass list of properties, if I remember correctly. Does that make sense? So again, the whole idea of G is the area so far. So if I figure out the first step and then I go another step, I just have to figure out the new area and add it to what I already got, because it just keeps accumulating area. So what is it about the shape from 1 to 2?
It's a rectangle.
Good. So there's another rectangle. We know that area is 2. And then there's this triangle.
1.
It's 2 tall, yes? Not too damn tall, but 2 tall. And 1 over. So what's its area? 1. So what's G of 2 then?
5.
What did I get? Hold on, let me catch up to you. So this equals 2 plus 2. Yeah, I'm going to catch up to you, don't worry. 2 plus 2 plus 1. I love it. Thank you. I didn't think you'd jump all the way. All right.
Well, you got to G of 2.
I know. I'm there. I'm with you. All right. So you can do the beautiful thing, because integrals, these guys, are all about areas. And now we know if I set it up as a function, g of x, it just tells me the area I've picked up so far. So of course, if you pick up so much area and then you add a little bit extra, you just have to focus on the new area and add it in. Now real quick, what's a little bit unrealistic about this function we're working with? I mean, how did they make this function? Why is it relatively easier? It's a bunch of freaking straight lines every damn where, yes? What kind of function would this have to be?
A piecewise.
Piecewise function, kick-ass.
Yeah.
So from 0 to 1, it's flat. From 1 to 2, it's a line going on, blah, 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 blah. Okay. But of course, we do this because we just want to understand the idea. And then we're going to build up, what do I do when it's all curvy? Okay. Let's see, what's g of 3 going to be? Well, it's going to be g of 2 plus, see if you guys are cool with this. It's going to be g of 2 plus what I pick up after 2. So it's the area up to 2 plus the area that I pick up from 2 to 3. I like it. So if I just focus on the area from 2 to 3, what's going on from 2 to 3? Got a big ass triangle. How tall is it? 4. And it's 1 wide, so its area is 2. So I get g of 2 is 5 plus 2, I get 7. Oh shit. This kind of makes sense. The g is continuously increasing. Why does that make sense? Because this function so far has had positive area, correct? That function so far has been above 0, so I keep adding more area. What's going to happen now when I step past 3? Negative area. I'm going to lose some of what I've accumulated so far. So if this was a velocity function, all right, so somebody's traveling at constant velocity, so they're going to pick up some distance, yes? And then they step on the accelerator because their velocity is changing now. Are you with me? So they're going to pick up even more distance. And then they let off the accelerator and they come to a stop, right? And they'll go, oh shit, I forgot something at home. So now they start coming back. Now they're going negative velocity because now they're going the other direction. So I'm going to lose some of that distance that I picked up. Okay. So what's g of 4 going to be? Well, it's going to be g of 3 plus what integral will I write here?
G of.
No. What integral will I write here?
Oh, 3 on the bottom, 6 on the top. 4 on the top?
4 on the top. Oh, did I make catching up? Oh, they went to 6. Thank you. They did go to 6.
Wow.
Okay. All right. So now they do a big ass step. So it's going to be 7 plus, what do I pick up from? So now 3 to 6, there's a couple of shapes, correct? But the nice thing is it's just purely the area. So here I've got a triangle that's 2 by 2. So what would that area be? Say again?
Negative 2.
Good, negative 2. All right, so that's negative 2. And now I've got from 5 to 6 is a rectangle, yes?
1 by
Yeah. There's another negative 2, right? So where do I end up at then? 3. Okay. I like it. All right, so you're going to have to do number 2, and now you know exactly how to do that. Yes? Let's see, what else they asked me to do. And what interval is g increasing? So let me kind of summarize what we got so far. Okay, so this is what we got for our areas. I do have to do this, yeah, okay. But you can tell, you don't even have to look at your outputs. How course, you know this. What's the instant that g is going to start to decrease? What's the instant that the area is going to start to decrease? At x equal to what? Or at t equal to what? 3. I like it. Did I use x's over there too? At t equal to 3, it's going to stop accumulating area and start losing area. So g is going to start to decrease at that point, right? So that's a relatively easy question. On what interval is g increasing from 0 to 3? Where does g have a maximum value? That should also be pretty straightforward. If you remember, where does a maximum occur? When it's increasing and then it starts to decrease. That's the maximum, correct? So basically, we just answered that question for an input when x equals 3, yes? Because the instant you go past that, you start losing some. So of course, that's going to be your maximum area. And then it says sketch a rough graph. So that's where you could do, I guess I did right. I don't want to use t's here. That's where you could just plot these, kind of connect them. You guys okay out there? You just plot these points, kind of connect them. Okay, all right. So that's the first step, is we created a function based on the process of integration, of finding areas, right? That was a new thing. We hadn't done that before. Now we want to start to try to see how does this connect to antiderivatives. And the interesting thing is, the first step we're going to do, let me remind you, we've got this. You just put an A. Aw. Poor little dude. There we go. Oh yeah. Okay, good. So I've got this guy. What I want to do, what do you think, now that we're in calculus, has anybody ever seen this function ever in your life before? Some of you guys maybe. But the minute we learn a new function, in algebra, we would have immediately learned its inverse, correct? That's sort of what we're going to do here, but in a really kind of roundabout way. Now that we're in calculus, if we had a brand new function, the first thing I want to know is what's its derivative. Yes? We had all these functions, so we introduced the idea of derivative, and then we should have been like, well, what's the derivative of every function I've ever seen? Can we do that, please? And we did. We basically did that, right? Now we can take the derivative of almost anything. So now that we have a brand new function that we never knew existed till now, the first thing we should ask as calculus students is, what's this thing's derivative? Right? That's fantastic. Let's build it up to that point. And that's not quite right, but that's okay. Thanks for playing. So we've got this set up. So let me kind of draw this picture again. I feel like, I remember I had a teacher that every class, he drew the same exact picture. Every class, he drew the same exact picture, and we sort of joked him. And now, thankfully, it's just this one class, but I'm going to draw this picture multiple times. So here I've got my f of t. Why did I draw this so small? Let me make this big. All right, get out of here. I want some room to play around in. Okay. And I probably want it focused. There we go. Okay. Hi. Okay. So here's my f of t. There's my x. So wouldn't this be, this would be g of x. Is that cool? All right, not fascinating. This is basically just a visual of what we do with this function here. Become an a. Okay, now, what is the, all right, let's look at it this way. Let's look at it this way. I have a function g of x. Oh, you're going to love this. How do I determine its derivative? Yes? Keep going. How do I determine the derivative of g of x? What do? The limit as h goes to 0 of g of x plus h minus g of x over h. Okay. So this is the thing that I want to be able to do some. Now, imagine, if I try to attack that directly, what the shit, right? We just learned this function. I have no idea. I'm not going to be able to factor it, right? And try to kill the h, correct? So we sort of have to attack this a little bit from the side. Okay. So what I mean by that is, let's kind of break this thing down a bit. So this would be what g prime of x is. So let's think about what that means visually. So let's go back to the visual. Here's x plus h. Is that cool? I'm just going to put it right here. It's just going to be a little bit above x. So we are sort of assuming h is positive. But what are we going to do eventually? We're going to make h go to 0. So effectively, everything we discussed is the same. And something you guys never really probably noticed but didn't really want to think about was this doesn't say from above, so h could be negative. It doesn't matter. As long as you're going towards it, you're going to get that derivative at that point. Okay, so but just for convenience, I'm going to put it here. So how much will the area change? That's really what the question is, right? How much will the area change if I go just a little bit further? Isn't that what a derivative is? A derivative will tell you how much will your function change. If you just go a little bit further in the x direction, how much will the output change? So what is the output of the g function geometrically? Ooh, I love that question. What is the output of the g function geometrically? Say again? Area, right? The output to this function is the area. So really, when I say how much will the g function change from x to x plus h, I'm asking how much area will the area change. Okay, now watch this. Okay, that should be very familiar. I've just drawn a little rectangle, right? Like Riemann sums. Can somebody tell me what the area of this rectangle is? It's going to be interesting. Yeah, how wide is it? Let me put it up here. So it's h wide. And how tall is it? Yeah. Isn't it f of x tall? Yes. Especially the way I drew it. And did it really matter what endpoint or whatever? Because again, I'm going to let h go to 0. So no matter what I do, it's going to end up being f of x because it's going to get smushed there. So the area of the little extra piece, let me see. Am I doing this in a different order? No. So this, the area up to here minus the area, so the area up to here minus the area up to here is going to be equal to, approximately equal to, are you running out finally? Damn it. Hold on. This little pen's been going for like, feels like 8 years. All right, it's finally dead. It's finally gone. I really want this to make sense. So I'm capturing exactly what we just said. The difference in the area up to x and the area up to x plus h is going to be this area in that rectangle. So what is the area of the rectangle? It's just h times f of x. Will h ever be 0 in what I'm going to do to it next? H will never be 0 because I want to let the limit h go to 0. It's never 0. So can I divide by h? So the limit as h goes to 0 of g of x plus h minus g of x over h is f of x. So that means that the derivative of this new g function is this. Now, I don't know if you guys are with me. So one way I like to think of this is, let me see if you guys are cool with this. Say this is an actual physical, like an actual, I have to give it 3 dimensions. Like a box up to here, correct? I've got a box up to there. And then I want to go like an infinitesimal step up. So I basically put like a layer of very thin tape on this side. How much area did I just add? Basically f of x. If I just put a thin layer of tape right here, I just added this much, f of x much area to it. That is why the change in my area function is equal to the function at that point, the function value at that point. That's what we just figured out. This is kind of huge. Using notation that we've used so far this semester, what does that mean g of x is? Let me see. This is a weird question. Yeah, right? If g prime is little f, g must be the antiderivative, which we represent as big ass F. Now, is this correct? It's not quite right. What's missing? That thing that, oh, yeah, dude. Okay. Okay, all right. So we got the first part of this down. You see, I got a little ahead of myself. Yeah. This next part you're going to be really excited about. I think, do I want to do that? Yes. We could do this. Yeah, okay. I could write this also like this. Are you guys cool with this? It really doesn't matter what side I put the C on. Are you guys with me? Now, in one sense, this would be 2 different C's, but I don't want to stick too much with that. Okay. Now, what we just did is very surface level, right? And you guys might think what we just did was we proved something. We didn't prove a damn thing. We just showed really good evidence for this. So what we're about to do is actually prove it. Holy shit. And what this process is called, what we just showed, sort of, we showed evidence for this, and it's called the fundamental, oh shit, the fundamental theorem of calculus. You're going to love this next part. Part 1. It's like history of the world, part 1. What I affectionately call FTOC 1. I'll make that a 1. So I just call it FTOC 1 to be quick. Fundamental theorem of calculus, FTOC. All right, so that's basically what we just did. So what it says, I'm going to write down what it officially says, and then we're going to prove it officially. Okay, and dear God, understand what we're doing right now. It's kind of gross, but it's making this connection so then we have some shortcuts we can start applying, and we have some shortcuts we can start creating, just like we did when we transitioned from the limit definition of derivative to the shortcuts, right? Where's this in the book? Yeah, part 1 is on page 394. Did I write that part down? Yes, thank you. All right, so if g of x is the integral, oh shit, I'm so used to putting a b up there. The integral from a to x of some function, f has got to be continuous for this. You can, if it was a finite number of jump discontinuities, you could just break it up from A to the first jump, and then from that to the next jump, and they each would follow the fundamental theorem. So it would still apply even with a finite number of jump discontinuities. Okay. All right. Now this is going to be neat. Help me out. What is g of x plus h? Don't overthink it. We know what g of x is, so what's g of x plus h?
X plus H on top.
Yeah.
A.
That's all it is, right? Just change the input. So then g of x plus h minus g of x would be the integral a to x plus h minus, okay, nothing amazing so far, right? Oh, whoop-de-doo. And of course we know why I put this down here. I'm trying to work my way towards the derivative. Now, does anyone remember the property if I want to turn these around? And by the way, quick side note, just to remind you guys, side note. Couple things. Do you guys remember? Okay. Wouldn't the integral from a to b for this little dude here, wouldn't that equal the integral from a to c plus the integral from c to b? So all I'm saying there is exactly what we just did several times, which is to get from one side to the other, I can add the first little area plus the next little area. I can break up my areas as much as I want or need to. Okay. Nothing amazing. And the second thing is, what if I wanted to change the limits of integration? What if I wanted to change the order of these? What happens if I change this from B to A? It's the negative, of course, because now instead of B minus A, it's A minus B, so the whole thing will be the opposite sign. Okay, now, with those two facts in mind, those are two properties we talked about already. Did I can rewrite this as first step plus okay, this is fascinating. All right, and I'm just going to write more than I really have to, just because. Oh, I guess I don't know. Oh, yeah, I do. X to A. I'm just going to reorder these. So then I can use that other thing from X to A, and then from A to X plus H. I can just write it, smash it together. That's got to be the total area from X to X plus H. That is what g of x plus h minus g of x is. So that's the first little result. Let me stop for a minute. Again, this is just the technical work to show what we did visually a minute ago. This is just highlighting that little rectangle piece. That's really all this is doing, but this is what it looks like fully fleshed out. Keep yourself straight, Jeff. Where are you at? Where are you at? Oh, you wrote on it. There we go. All right. Now, how are you guys doing? All right, we got time. So I got here. Let me see. I'm going to keep going. By the way, I love, anyway, you guys can keep taking notes if you want to. You're not going to have to do this yourself. But now, what kind of makes sense now is, all right, so let's do a couple things. I do eventually want to talk about this. So I have to divide both sides by h. I know I want this to be there, because that's what I'm fundamentally trying to find, the limit of that to get g prime. Is that cool? So then I divide this by h. It's just a little bit better to look at it as instead of underneath this whole thing. So for just a minute, let's look at just this piece. So this is what I eventually want. So then I can actually apply limit and figure out what the hell it is. Let's look at just this piece right here for a minute. And we remember, and just to remind you guys, f is continuous on a, b. If f is continuous on a to b, right? And I don't know if it's like this, or if it's like this, or it's like that, or whatever. Doesn't that mean, so if you've done any of the homework, you're very used to this, does that mean that somewhere there's a small m, like a lowest output, and a big M, and a largest output? And maybe if it's just a constant function, then little m equals big M, and who cares, right? But somewhere, if it's continuous between these two, there's definitely a lowest value and a highest value. Right? That's the good old absolute extreme kind of stuff. Yes? Okay. And again, it might happen in the middle, right? Like Rolle's theorem kind of thing. Yes? Okay. So somewhere there is a value. So let's say there exists a C that's in here, and a D that's in here, so that f of C equals little m and f of D equals big M. Okay? And I want to say this. Oh yeah. Let me see. Do I want to write? Yeah. Recall. I'll do this. Recall this property of integration. I think it's the 8th one in the textbook. Some of you guys should know where I'm going, maybe. This integral has to be between m times b minus a, and I should say more than m, little m b minus a, and big S m b minus a. So that's the thing I was saying. Did I say that when everybody was here, the whole thing with the big rectangle, small rectangle? I think I did, right? So that's exactly what this is. Okay. You guys are doing great. What is b and a in this integral? Yeah, x and x plus h, correct? So what is b minus a? It's just going to be h. Is that cool? And not surprisingly, I'm going to divide by h, but let me remind you, what was little m and big M? Where did they come from? I don't know if you guys really noticed this is a huge part of this. Aren't they obviously outputs of the function at some point? Yes? At some point the function gets its lowest and its highest. So let me bring that back into play. This will be h times f of c, m times f of d. Holy shit. And where were C and D? I did a horrible job. I did a horrible job.
What, you mean h times f of d?
Say again, sorry?
You mean h times f of d?
No. Oh, here, yeah. Thank you. I should have been a lot more precise up here. We've kind of, do you see how I did this and this and this? What are A and B in this problem? I just wasn't specific enough. What are A and B at the moment? X and x plus h, correct? All right. So, I'm going to divide, remarkably enough, let me bring this whole thing back in. Okay. So I divided everything by h. So let's go back up to what we're currently working on. We are trying to analyze, we're trying to do stuff with this. Didn't we just get this here? So now watch this. What is the limit as h goes to 0 of all these pieces? Well, the pieces on the side. So now we're going to apply squeeze theorem. Because the thing in the middle, I have no freaking idea how to analyze it, correct? And you're all like, I don't know how to analyze any damn part of this. All right. Somebody remind me what I just made a point out of. Where is C? Between what and what? A and B, which is x and x plus h, correct? And D is in the same place, yes? So, what happens if C is between x and x plus h, and I let h go to 0, what is C going to go to? X, not 0. C is between x and x plus h, somewhere between. And I let h go to 0, which means this is going towards x. That means that C only has x as an option eventually. So this limit is f of x. And the other side, same damn reasoning, yes? So if f of x is less than this, Jeff, and f of x is greater than this, then this equals f of x. That's the squeeze theorem, right? So eventually it comes together, so the thing that's in the middle has to equal that value. Okay, this is really weird. Okay, so let's come back up. So we just figured out, here's what we just figured out. Because you're all like, I don't know what we just did. We just figured out that the limit as h goes to 0 of 1 over h integral x to x plus h, I'm giving a running commentary, we just figured out that this equals f of x. So therefore, recall g of x plus h minus g of x over h is 1 over h. All right, let's see how. Okay, everybody's still looking at me, even Ben, who's shrinking. Okay. Right, this is what we wanted from way back here. We wrote this, and we're like, okay, we've got to do some work. Now it can replace, now it can say what happens when I do the limit of this. Well, this side, of course, is g prime. And this side we just showed is f. There we go. So I'm almost certain some of you guys could have just, would have been fine if I had never done all that. But I gotta show you. Because again, it's nice. I actually don't care how you feel about it. It's just good for you to see stuff like squeeze theorem, what it's really good for. Plus, you really should at least see, if not fully comprehend every step of, but at least see the proof. Because this is one of the most important things in calculus, right here, right now. And of course, let's keep going. Because if there's an FTOC 1, there must be at least an FTOC 2, a fundamental theorem of calculus part 2, and that's thankfully that's it. Okay, so remind me, what does this mean about big ass F? It must be G plus C, right? Okay. And remember, recall, G of X was this, right? Okay, just remember what the hell G was. So tell me, what is g of a. Zero. I like it, because then it would be a to a, no area. I love it. Now, let me see, where should I put the line? Let's put the line here. Sure. So help me out now. Big ass f of b minus big ass f of a. All right, this is not hard, right? What is big ass f? What's the only thing we know about big ass f right now? It's equal to this thing, right? So what's big ass f of b? G of b plus c, yes? Jeff, there you go. And what's big ass f of a? I like it. And don't the c's cancel? So I got g of b minus g of a, but g of a was 0. And what's g of b? What would g of b be? G of b, what would it be? What's g of b? Here's g of x, so what's g of b? Here's g of x. What's g of b? Here's g of x. What's g of b? Here's g of x. There we go. Just put a b in, right? I don't blame you guys. Trust me, I do not blame you guys. You're right now like, I kind of know how you feel right now. I do. I really do. Even though I'm the one doing it to you. I understand how you feel right now. But we are there. What the shit? What, Jeff? What? What did we just figure out? This is kind of huge. And again, remind me real quick. Does it have to be T? Couldn't I have picked M? Couldn't I have picked W? Couldn't I have picked? So let's replace this with freaking X. Let's go back to normal. Yes? So what we just proved, and what I appreciate most of you at least watching happen, is we just proved that to do an integral of a function, I just have to find its antiderivative and plug the upper limit in and subtract the lower limit. So, stay with me. Let's do one we could do geometrically, and then I'm going to show that this is true. This is huge. I don't know if you really understand. You probably don't. You're like, I don't know what the hell just happened. We just made the connection. I don't have to do, at least once you're out of 5-2, you don't have to do the infinite sum process to find the area. Isn't this asking for an area? And what is big ass f? Antiderivative, which for a lot of functions is not too hard to find. But for a lot more functions is very hard to find. But we'll get to that. Okay. So, help me out here. What would this be? Can you just graph that real quick for me? What shape do I get here? We did this before, I think. All right, don't I get a little triangle? Yes? So can you just tell me what the answer is? Yeah, so this should be 1/2, yes? We already know it because it was a really easy function. It makes a really easy geometric shape. The minute I make that x squared, you can't do this shit, yes? Now, let's test this thing out. So what this is saying is, I could figure this out by figuring out this guy's antiderivative. What is the antiderivative of x? Beautiful. And let's go ahead right now, we'll just put that in there. Yes? You'll notice something. This is why students start to forget the plus c, because of what we're about to do. And here's how I designate this. What am I supposed to do with this? I'm supposed to evaluate it at the endpoints, right? That's what this says. And then find the difference of those. So the way we kind of show ourselves, we still have work to do. This is just f. But I want to evaluate it from 0 to 1. So that line means this function evaluated between 0 and 1. So now I'm going to do this at 1 minus, right? Antiderivative at the top, limit, minus antiderivative at the bottom, limit. So 1/2 of 1 squared is 1/2. The c's cancel. 1/2 of 0 is 0. Did we get the right answer? Yes. Okay. All right. Maybe. Before section 5.3, how would you have had to do this? You would have had to set up the summation. You would have let limit n goes to infinity. You would have gotten your I shit, and then you would have done the shit, and then you would have done the shit, and it would have taken like 2 pages, yes? And now look, this is how much room it took me just because I was writing big, right? And that's kick-ass. Okay, maybe. So let's do a different problem with time. Oh yeah, time. This is so awesome. Some of you guys are like, it's not awesome. Shut up. It's too bad. All right. So what if I had to do this integral? What do you got, Jeff? I didn't really think about it. Oh yeah, that's a good point. Let's do. And the thing I forgot to say, so remember, the definite integral, this is a definite integral. We're going to do indefinite integral eventually. But with the definite integral, what always happens are the c's are always going to cancel. Do you guys agree with me? Because the big ass f is going to have the same plus c. It's going to always cancel. So you don't have to write plus c for a definite integral, and that's why students start to forget it in general, because sometimes you don't have to write it because it's going to die anyway. Okay. So help me out. I made this not too bad. What is the antiderivative? Yeah, now we don't write the plus c. If you want to, you can. You just have to understand you only don't have to write the plus c when it is a definite integral. What do I mean by definite? It goes from a number to a number. Indefinite is going to be when I just have an integral with no limits. So we're going to do that later. Then the plus c has to show up because it doesn't have any difference to do. And I want to evaluate this between 2 and 5. So now I just got to plug shit in. This is awesome. Do you remember how long it took us to do that sum and the limit is n goes to infinity? You remember how long it took us to do that? Yeah. So look, we're almost done. We're basically done. So if I plug a 5 in, 125 minus 50 plus 5 minus, and this is where another place where students are going to mess up is you got to subtract everything you get when you plug a 2 in, of course. Somebody make sure I did that right. Let's see. I don't trust myself today. 8 minus 8 plus 2.
78.
Yeah? So yeah, we get 75, 80 minus 278. I love it. Kick ass. And finally, the pièce de résistance. If you have your calculator, I can't remember, I think I showed you this already, did I? The way to make the calculator do the area? Did I show you that? Let's do that one more time. What was this? 3x squared minus 4x plus 1. I'm going to hit zoom 6 just to make sure I can see what I want to see. And then I'm going to do something else. All right, is everybody with me on this? Let me hit zoom in. We've never really done that. Let's see if that does okay. All right, that's not going to be good enough, Jeff, because now, shit, screw that. Don't do that. Hit zoom 6, my bad. I got to go up to 5. I just forgot. All right, so now let's do second trace to go to calc. And I want to calculate the integral. And it's going to ask me for a lower bound, so I'm just going to hit the number 2. On the upper bound, I'm just going to hit 5. And then it's going to actually show me the area. And thankfully, it's 78. Right? This is a beautiful way to check your work. Yes? It's kind of nice, right? Okay. Yes.
What did you hit on trace?
Oh, second trace, and then you should get this, and then number 7, of course, is the, yeah. I like it. I like it all. By the way, number 6 does exactly what you would hope. If I put a 1 in, it tells me the derivative at 1. Yes? You guys kind of with me? So derivatives tell me the instantaneous rate of change, right? The slope at that point. The integral tells me the area I've gotten up to that point. But today we proved that they are inverses of each other. Take a derivative to find that derivative and take an integral to get back to the original function. They undo each other. Okay, funkydelic. Funkydelic. I think I did. Yeah, okay. All right. There's one more thing, but I think that's enough for today. What do you guys think? We did a lot.
Yeah.
You guys suffered through a lot. Did everybody get their updated grade sheets back yet? The grade sheet I gave you last time did not include your test 3 grade in the average. Aldo. Jake?